Hi, I'm Joris, and I'm going to present this talk together with my colleague Dewey. We are both from Voltron Data, um, both working on the Apache Arrow project, the open source library, and we're both also involved in the geospatial ecosystem. I'm involved in some packages on the Python side, for example, GeoPandas, and Dewey is involved in the R spatial packages. So in this talk, we want to explain to you how Apache Arrow is also very relevant for the geospatial use cases and how you can use it to accelerate geospatial computing. But let me first take one step back to the Apache Arrow project itself. Apache Arrow is many things, but at the core, it's a standardized in-memory format to represent tabular data. And by having this standard representation, we can improve the data interchange, we can improve in-memory processing in many different languages. So for example, for the data interchange part, currently there might be several languages having implementations to read some data file to get it into memory. But then also if you want to move that data, for example, from Python to C++, again, that might involve some conversion and serialization costs. And that's one application of having a standardized in-memory format that we can, once the data is in memory, much more easily move it from one system to another with reduced serialization costs. But also we can, if you have an efficient implementation to read certain file formats, we can also share those implementations because those different languages can connect to Apache Arrow memory format. A very specific example of this is the, for example, the Parquet file format. The Apache Arrow project has a good implementation to read such files, and so both the R and the Python bindings to Apache Arrow use the same implementation under the hood to read this file. It's not only to get data or to move data around, it's also a memory format that is efficient, laid out for to actually use it for computations. So it's for columnar data, for tabular data, and very specific about the Apache Arrow memory format that is that it's a columnar memory format. So we have the data of the same data type in a certain column all stored together, so we can efficiently compute on such data. So Apache Arrow enables lots of use cases and possibilities to improve the data ecosystem, to have faster access to interchange data both over the network, inter-process, or within process, as a in-memory data structure to do computations, to share implementations, and all those benefits, they perfectly well apply to geospatial data as well. So specifically for tabular geospatial data, so if you have vector geometries where you have attribute data linked to those geometries, so then you have a table, and you can represent that data as in Arrow memory format. So for the rest of the talk, we are going to go into some of those example use cases, and specifically for geospatial data. I'm going to start with explaining how Parquet, the file format, can be used in the geospatial context. So what is Apache Parquet? It's a open source file format. It's available in many languages. More specifically, it's a column-oriented format, so that makes it a very good fit with Apache Arrow. It supports lots of different data types and complex nested data as well. It has some very efficient compression scheme, so you get very small files. But so it's a file format that is already used widely in practice. Typically, if you have large amounts of data and you have an analytical read-heavy workflow on top of those data, it's also often used in a cloud context. So we have this file format, a very useful file format, and we want to bring this into the geospatial world as well. And that's where GeoParquet comes into the picture. So what is GeoParquet exactly? It's an effort to standardize how we are going to store geospatial data, and specifically vector data, in the existing Parquet file format, so that we ensure that different people and systems that want to do this in such a way that it's interoperable and that we can share those data. So it's using the existing Parquet file format. It's not changing anything to the file format itself, but it will standardize how we're storing the data, the actual geometries in it, currently using the well-known binary format to store the geometries, although there are also plans to expand on this. We will talk about that a bit later. We also standardize the metadata, so we can store all the information that is needed to interpret the geometries correctly. So how they are stored, which coordinate reference system it's using, the geometry types, whether they are planar versus spherical coordinates. So all this metadata is stored inside the Parquet file. A few examples. I'm using Python and R here because Dewey and I are R and Python developers, but you can also read this in other languages as well. So there are already packages that you can use to read such files. And I'm including here a small benchmark using, in this case, in Python, GeoPandas and PyArrow under the hood to read a Parquet file, polygon data set of buildings. And I'm comparing it when I read it with GDAL using the PyOgrio Python bindings to GDAL. And you can see on the left graph that reading a full file, the full file, is quite a bit faster for the Parquet file compared to some of the standard geospatial formats such as GeoPackage, shapefile, and flat GeoBuff. That's the case for the full file, but especially it's especially the case for a single column, which shows a bit the benefit of having a columnar file format. So the benchmark of the single column, in that case, I'm reading a single numeric column from the file, and you see that for Parquet, it's very fast to do that. On the right, you also see a visualization of the file size. Of course, there might be other ways to further compress those files, but by default, this is what you get when writing those files, where Parquet also gives you a very small file size while still being able to read it very fast. Of course, benchmarks are always flawed, and so yeah, it will depend a lot on the exact characteristics of your data, of the geometries you have, etc. But this gives a bit of an idea of the potential for the Parquet file format for geospatial data. It's a very young project still. GeoPandas has it for some time to read it, but last year we started an official initiative in the Open Geospatial Consortium to standardize the efforts. We had the first release earlier this year. We have several people involved from several open source libraries, but also from some companies in this space. What we need to work on is further expanding the support for this format. So it's actually already included in the latest GDAL release, so in GDAL 3.5, which will also enable other systems that use GDAL to read files to potentially read GeoParquet files. There are libraries in Python, R, and Julia to read them. There is work in progress in some other systems such as Apache Sedona, Carto, and others. We will also try to see more usage in actual data that is stored and shared online. And for example, the Microsoft's Planetary Computer data catalog is already using GeoParquet for some of the files that it's sharing there. There are certainly more things to do. So something that's currently not yet standardized, but it's certainly an interesting topic, is how to deal with data partitioning and ensure that we can do spatial indexing both in this partition data set as within a single file, so that we can improve the efficiency of spatial queries on top of Parquet. And in general, we need to stabilize the specification. It's a very young project, so feedback is very welcome. You're very welcome to join the conversation at the GitHub repo for this. I want to get back to, before handing it off to Dewey, to the benchmark that I showed before. So I showed that using GDAL was quite a bit slower to read the GeoPackets or shapefile or flat GeoParquet file compared to PyArrow. But this is not so much the case, because those file formats might be slow file formats in general, or that GDAL is not reading them efficiently. So for a large part, the reason that it's much slower to get this data from those file formats into Python or our memory is because the transport, the interchange from GDAL memory to Python memory is quite slow at the moment in the current implementations. So how does Python and GDAL interact? GDAL has a get next feature API where Python can each time ask for the next row and the data of the next row, but you have a lot of overhead in creating those feature objects, in moving that data to Python, and then Python needs to build up from that its columnar memory to store it in Python memory. And that's one of the use cases of where Apache Arrow promises to improve this, to have a standard format to move data around. And so we can use Apache Arrow here, and we could improve and make it much more efficient to read those existing file formats into Python or our memory or other systems, where GDAL could directly, while reading, construct an Arrow memory structure, and then that can be moved very efficiently from GDAL to Python and R. But how this works in the technical details, that's something that I will let Dewey further talk about.
Yeah, thanks, Joris. So I'm going to talk a little bit more about some of those details. And just as the GeoParquet format is an effort to leverage Parquet file format, which has wide support and is very fast. The GeoArrow initiative that I'm going to talk about is a way to standardize how that happens in memory. So once GDAL reads a file, once the Apache Arrow library reads a Parquet file, what happens when that comes into memory? So right now, I work a lot with the SF package. It's one of my favorite packages, and I work in R. And in the SF package, it uses all of these other spatial libraries. So it uses GEOS to do lots of geocomputation. It uses PostGIS to do some geocomputation, and it can read directly from there. It uses GDAL to read many of the file formats. It interacts with QGIS in some ways and GeoPandas in some ways. But every single one of those interactions requires quite a bit of code. So it has to use GEOS's API to transform its geometries in a way that GEOS can understand it, and then a way for GEOS to read that vector of geometries. The same goes for all of the other types and all of the other libraries. That takes a lot of work. And so the vision with GeoArrow is once we have this file in memory, or once we have this geospatial data in memory, we have one array format that it can be understood by all these libraries. It's an in-memory format, and so it makes those interactions a lot easier to define. So that graphic that Joris showed, where we look at the GDAL library and how the GDAL library can leverage Apache Arrow to get data into the Python and R libraries very quickly. Not only is it very fast, but it also reduces the amount of code that it takes to like a couple of lines. And so this is building on some work that done by Evan Rouault, who's one of the main GDAL maintainers. And recently, Evan made an RFC into GDAL, proposing that there'd be a way to get GDAL's data into other libraries using the Arrow C data interface. So the C data interface part is important because that is a way to define how to get at that memory in Arrow format. It's ABI stable, and so it's able to minimize a lot of those interactions that take a lot to maintain. This is just an example, and it's not all that much of an exaggeration of how much code it takes to open pretty much any file format that you can think of. GDAL has a lot of drivers for a lot of file formats. And this latest RFC is a proposal to be able to output an arrow array string. So that is one of the in-memory formats defined by the C data interface. And it basically opens up interaction to GDAL to a lot more libraries. And those libraries are numerous. So Arrow has been around for a while, and it's really good at dealing with tabular data. And at the heart, that's what GDAL is doing. It's reading in a table of data. So we have the C++ interface, the C++ bindings for Apache Arrow. There are bindings in Rust and Python and R and many other languages. And on the right, there's a whole bunch of projects that use the Apache Arrow columnar format or the Apache Arrow library itself to do fun things like an entire query engine, like the Acero query engine, or Data Fusion, which is another attempt at a query engine based on Apache Arrow. There are database connectors. There are ways to send these arrays between processes. There's a very rich ecosystem once that data is in Arrow format. So this RFC is something that we're really excited about because it is an example of how the geospatial world can leverage the in-memory Arrow format. One of the problems is that GeoArrow or Arrow itself is very good at putting tables between processes and into memory. And it's been around for quite some time and has ways to encode integers and strings, nested lists of those things, times and dates. Pretty much anything that you'd find in a table, Apache Arrow has a way to encode. And Joris mentioned earlier that we're using the existing Parquet format to put geometry in. And we're using a binary format for that. So we're putting it in as a byte array. So that's okay. But it turns out that that actually is, once you start to get into the really low level algorithms that, that form the heart of the geospatial and the geocomputational world, that starts to get very slow and inefficient. And Arrow has this huge variety of format that has nested lists of numbers and integers and arrays. And if you can encode geometry in that form, you can actually speed up a number of workflows. And we're going to show some examples of that. So right now, well-known binary is probably the best example of how that is done currently. But if we can do that using the Arrow native types, we can make things a lot faster. And so I put this link at the bottom. The GeoArrow specification is this effort of ours to try to formalize how this is done so that we really can have that one GeoArrow array sitting in the middle of all these geospatial libraries. So here's an example of that for a point. So if you have a vector of points, this is 4, for example, and you want to store those in Arrow format, instead of serializing that to well-known binary or text like I did at the top, we can line up all those coordinates. So in this case, we've got 0, 0, 2, 0, 0, 1, and 0, 0. We line up all those coordinates in a row. And because it's a fixed size list, which is an Arrow native type, we know how to get to every single one of those depending on what point. So if we want to get the 3rd point, then we're going to hop to the 6th number and read the 6th and the 7th number, and we have our coordinate. If you want to encode a line, you have to find a way to get to the start of each line. So in addition to all those coordinates lined up, we have a vector of offsets so that we know how to get to the first line, the start of the first line, and we know how to get to the start of the second line, if there is one. And in this case, we're only encoding one line, so we only have 2 offsets. And the same goes for a polygon, but because polygons can have multiple rings, we need one more layer of nesting. So the idea here is that we have random access to every single coordinate. If you know what ring you want and what feature you want and what vertex you want, you can get to that coordinate without having to walk through the first every coordinate before that. And so that's the main difference between well-known binary and the GeoArrow format, is this random access. And if you do some benchmarks with some algorithms, it actually turns out that this is really fast. So, for example, something like GeoS has a format like this where they have random access to all the coordinates. And as you can see, it's way faster than well-known binary to calculate the length. This is just a length that's walking through every pair of vertices and performing a relatively cheap computation. So with well-known binary, we have to walk from the beginning to the end. And because we don't have random access to every single one of those coordinates, we have to do a bit of copying. And there's some games you have to play to get that to work. Those games take a lot of time. So it's almost an order of magnitude slower than GeoS's implementation. The really exciting thing about this is that how much faster GeoArrow can be than even a pretty optimized format. And the reason that it's that fast is because compilers are very good at optimizing when they have access to that memory and they know how that memory is laid out. So earlier on, Joris mentioned that the Arrow format is designed for modern hardware, and it's designed to be fast for analytical workflows. This is an example of how that can manifest itself in the geospatial world. So this is the kind of thing that's really exciting for all of us, because not only is this can it reduce the amount of code that it takes to interact with some libraries, we can also write much faster algorithms because we know exactly how that memory is laid out. So putting this all together, Arrow is an example of a query engine built on Apache Arrow. It's a streaming query engine, so it can take an arbitrary data source, and as long as everything can be put into that Arrow array stream format, it can walk through it and perform a query, whether that's SQL or whether that's something like dplyr that's defining the query. So here's an example. We're reading data from an S3 bucket. We're using the datasets API from Apache Arrow's C++ library, and we're running a dplyr query using familiar dplyr syntax. In this case, we're taking a whole bunch of parking violations, figuring out which are the most expensive ones to figure out what kinds of violations those are and where they might occur. And this works today. So you can run that on your computer, you can copy and paste it, and you can get this and you can see that there are a couple of different types of that. And if we want to do some further processing, like figure out where those violations occurred and make a map, we could do that. What gets us really excited is the ability to do some of those geospatial algorithms, which, as we saw, can be incredibly efficient because of the way that the memory is laid out directly in the query engine, which can already do things like perform these computations in parallel and stream data from remote data sources. In addition to having bindings in and being able to transport data directly into R and directly into Python, so that geospatial developers can spend more time making their geospatial code faster, rather than focusing on shuffling strings and integers around to remote data sources. So we've done enough to know that we have a lot of opportunity, and we're really excited about some of the initial adoption of this. And we do have a lot of work to do. And so we'd like to invite you to follow us on Twitter to keep up to date, and also to participate in the discussions going on around these specifications, which really form the heart of the work that we're trying to do.